So last time, I think we have talked about the subgroups. Let me just write this thing down. So I'm basically following the order in the notes that I have provided. So I have defined the subgroup concept. Now I'm going to define the product, right? Product of two groups, right? G and H, okay. So basically this is like, I mean, it's just a mathematically abstract way of defining the product groups. So, I mean, in set theory, for example, you know that the product of two sets is basically these two tuples, the set of two tuples, where G is from G and H is from H. Yeah, I mean, these kind of sets, okay, sorry, H is in H. So we basically define a group operation on this set, right? That's essentially what it is. So that means, like, for example, GH, an operation with, let's say, G prime H prime is the same thing as G operation with G prime, whatever that operation is, and H operation with H prime, okay? I mean, this is basically what it is. You can actually think of it like this. Let's see. Whatever, that's the definition in here, but in any case, this is the operation for one of the groups, that's the other operation. So in principle, I mean, they can be different from each other. Usually they aren't, but in any case. But instead of this, let's just forget about all these kind of things and then just forget about these showing the operation explicitly. So basically the product of GH pair with G prime H prime pair is the same thing as GG prime and HH prime. Pair from the GG prime and HH prime, right? There's no physical intuition in here. It's just a mathematical way of defining, let's say, new groups out of old ones. However, this is kind of useful because then you can analyze the structure of some of the groups in terms of smaller groups. So you can perhaps understand some of the groups better, like the three-dimensional rotation group, for example. This can be analyzed like that, right? You can actually think of it as some kind of a product group. As a result, I mean, these kind of things are kind of nice ways of actually understanding the structures of groups, right? So in here, I just need to add this. So the group G has some kind of an identity, and group H is basically an identity, right? So the pair of this tuple formed from the identities is the identity of basically the product group, right? So the products of the identities in a way gives us the identity. The inverse of this is basically given by this and things like that, right? Let me say etc. in here. Okay, perhaps what's important in here is that, let's say it like this, sorry. Let's say in the product group, G cross H, there is a special subgroup. I don't know how to call this like that. I'm just going to call it like this. So it's basically formed from the elements where the first element of the tuple is an arbitrary element of the group G, but the second one is just the identity of H. Okay, so G in the group. Let's say it like this. Let me call this like XG or something like that. Okay, so basically you can form a one-to-one correspondence between these elements and the group G in a way. Okay, so it's like the group G multiplied with the identity of H or something like that. Okay, so this is a subgroup. And what's important in here is that this is isomorphic to the group G. There's another special subgroup, so I'm going to call this as XH. So in that case, this is obtained by taking all elements from the second group and then, sorry, what did I do? All right, let me undo this. Okay, I didn't break anything, sorry. Taking, multiplying the identity of the first group with the whatever, all the elements of the second group. This is also a copy of the group H. In a way, you can actually think of it like this. In the product group, you can see the groups, copies of the groups, individual groups G and H, right? So basically, these groups appear as subgroups in the product group. Right? It can also be thought like that. There's another thing in here. All elements of XG commute with all elements of XH, right? So these two special subgroup basically satisfy the property that each one commutes with the group elements of the other one. So in a way, these are some signs where you can actually look for to understand if your group can be written as a product group, actually. So there's one last condition in here, one last thing that we can say. So let's say it like this. Any element, sorry, there's one more thing. All right, there are two more things. So the intersection of these two groups is basically the identity. Let me write it down like that. So that's the identity of the product group, right? So these two subgroups doesn't actually intersect at the trivial subgroup. And there's a fifth one, which kind of, yeah, let me also write this thing down. So any element of G cross H can be written as a product of an element from X and an element from Y. So X of G, an element from X of H in a unique way. There's also uniqueness in here, but once I stated this one in here, so this is something that can be proven easily, right? I don't want to go into the details in here, but basically every GH can be written as G multiplied with the identity, multiplied with identity coupled with multiplied with H, right? Something like that, okay? You can actually write it down like that. So this is an element in the first subgroup. This is an element in the second subgroup. Okay. So in any case, so these are actually some signs, some necessary things that you can actually check to see if your group is actually a product group or not. Okay. Let me just say it like this. Right. Let P be a group such that it has two special subgroups, two subgroups. Let's say X and Y with the following property. Properties. Okay, so the first one is that the X intersection Y, so these two subgroups, do not have any common elements except the identity. There are these two subgroups, X and Y. Their common element is the identity. So the second one is every element of X commutes with, let's say X commutes with Y. Right, let me just say it like this. This essentially means that, that's basically, by this I mean that if G is in X and H is in Y, then GH is equal to HG, okay? So probably X is not commutative. So elements within X do not commute with each other. Elements within Y do not commute with each other, but an element in X commutes with all elements in Y. So commutativity is important. The third one is, I think, this is the generator property. So any element of P can be written as a product of elements from X and Y, okay? So we say that like X and Y generates the group P, okay? So by using this, you can actually show that, right? This expression is basically unique, right? It can be written as a product of elements from X and Y, but you can do it only in one way, okay? You cannot have two different products giving us the same thing. Again, I'm not going to go into details in here. In that case, so in that case, basically P is isomorphic to the product of these two subgroups. Okay. You can then consider the full group as a product of these two subgroups. Okay. So in that way too, we can actually think of the a group as a product of two subgroups. There are a few examples. I'm just going to do it like this. First of all, for example, C6, the cyclic group with order 6 is, can be considered as the cyclic group of product of the two cyclic groups of order, let's say 2 and order 3. So let's say that C2 is, for example, identity and A, and C3 is the identity and B squared, for example. So A has order 2 and B has order 3, okay? I can then think about the symbolic expression like AB, for example, in the product group. So let's say it like this. In, let's say, C2 cross C3, I have a certain element of the form like AB pair, for example. I'm just going to call this as like shorthand. Yeah, let's just call this as C, okay? So C is equal to AB. Then you can show that C to the N is equal to A to the N, B to the N. And you can easily see that C to the N is equal to identity if N is equal to 6, for example, and that's the smallest integer where this thing happens. And so as a result, then you can actually see that C2 cross C3 can actually be written as identity. Well, that's basically the identity of this thing in here. Then we have C and C squared and so on up until C to the 5, right? Just check this. I mean, you can convince yourself that the product of these two groups, let me use a capital C in here, right? Okay, product of these two cyclic groups actually gives us a cyclic group of order 6. Okay, that's one example. Let's quickly go to the second example. C to cyclic group of order 2, product with cyclic group of order 2. As might be expected, this is not the same thing as the cyclic group of order 4. It is not. The reason is this, all right? Both of these groups have actually right, the cyclic group, so therefore every element has order 2. And so therefore the products of any elements would also have order 2. So all elements in here have order 2. So the square of all of the elements in here is equal to identity. But here we have actually 2 elements where the order is equal to 4. Okay. So as a result, this group is not the same as this one, but it's equal to the dihedral group D2. So let me just show you this. D2 is basically that group. I can actually think of it like this, where each element has, the square of each element is equal to identity. Let's see. And the product of any 2 elements gives us the third element. So as a result, AB is equal to C, for example, and AC is equal to B, and etc. Okay. I mean, you can define the group multiplication table like that. In any case, if you remember, this is the same thing as the symmetric group of a rectangle, if you remember. In that case, you can think of A, for example, as a reflection across the long axis, and B as a reflection in here along this axis, for example. And C might be considered as this, let me just write it down like that. C might be considered as 180-degree rotation, for example. Okay. And then convince yourself that, I mean, it's quite easy to see that all of these 3 operations have order 2. So if you apply the operation again, you get the identity. And the product of any 2 operations gives us the third operation. Just convince yourself that this is the group multiplication table in here. So it's the symmetric group of a rectangle. Let me repeat this again. Is the symmetric group of a 2-dimensional rectangle. Again, let's just remember that. I'm thinking this in 2 dimensions. In 3 dimensions, I can actually add more operations, 3-dimensional rotations and things like that, that would make this the symmetric group to be larger, actually. Okay, so what happens in here is that in this case, for example, this is a subgroup. Right, let's just call this as X, for example. So if you take the identity and any element, any non-identity element, this is a subgroup. Okay, and interestingly, these 2 subgroups satisfy the property that we have mentioned before. And so as a result, I can actually think of this D2 as the cross product of X and Y. Okay, I'm writing isomorphism in here because somehow I define the product of sets as in a formal way. So as a result, perhaps they are not the same, but they are isomorphic. You can actually think of it like this. But alternatively, you can actually define this as like the product of these 2 cyclic groups. So in any case, both of these are cyclic groups, C2, and the product of these 2 cyclic groups gives you, therefore gives you this dihedral group D2. This is also called as the Klein-4 group, if you, probably I mentioned this before. Okay, I mean, there are things like that, right? What else can I say about this? I don't think that I can say much, right? Let's see. Do you have any questions in here? Okay. There's not much can do in here. So let me not give any more complicated examples. At some point, we are going to need something simpler. All right. There's this rearrangement lemma. So there's some kind of a notation that we are going to use. Notation. Right. Let A AM be a subset of group G. Anything, I mean, it can be a subgroup or it does not need to be, right? I'm just describing a notation in here. Let's say G is in a group. In that case, by the notation G multiplied with the set, I would actually mean the set of elements that we are going to get, GA1, GA2, and so on, GAM, which is obtained by multiplying each and every element of that set by G from left, right? That's the definition. And A multiplied with G from right is the, obviously, is the, again, the set that you would obtain by multiplying each element from right by G, okay? So in any case, there's a few other things. So that's the definition in here. So first of all, this is the definition, okay? There's one more definition, all right? So let me add a, let me add a box in here, okay? So if there's another one, if B is another set, let's say B1 to BK is another set. In that case, we then define AB as basically all of the expressions that you're going to get AI by multiplying each and every element of AI BJ, right? There. I mean, the things that you're going to get in here, okay? So this is like the unions of whatever. I mean, I don't want to write this in an awkward notation, okay? So as a result, this is then what we have. Okay. Can we define something like A to the inverse? I can actually define it like this. So why not? Sure. In that case, but this is not a notation that is used frequently. Then by A to the inverse, then I would mean a set where all the elements are obtained by taking the inverse of each and every element, right? Let's just define it like this. Okay. So there are a few things in here. So first of all, associativity. Okay. I mean, let's just say it like this. GAH, for example, is the same thing as, well, first multiplying G with A from left and then multiplying this set from right. And this is the same thing as like GHH. And GHA, for example, that would actually mean this thing, or it can mean GH with A and so on. I mean, I can continue with this like ABC, for example. This is uniquely defined because this kind of a thing is satisfied and etc. Right? So associativity is okay. So I can also, I mean, from time to time, we are going to make calculations with these kind of sets. And so as a result, just keep in mind that the associativity is okay in here. No problem with the associativity. There are a few things in here. Another thing. So I think I'm going to make it like this. So GA has exactly the same number of elements as A. Okay, so what I'm saying in here is that, I mean, A is this M element set, let's say. In that case, GA also has M elements, and similarly, AG has M elements, right? What I'm trying to say in that case is that all of these elements are distinct from each other. Okay. So let's say it like this. A has this, like A1 to AM, M elements. So all AI are distinct, let's say. They are different from each other. In that case, in GA, all of these elements are also distinct, right? All GAI are also distinct. Okay. Basically, if it happens that GAI, one of these elements is equal to another element in here, GAJ, this would imply by the cancellation thing, I can cancel G's from here. That would imply AI is equal to AJ, which means that I is equal to J. Okay. So only from the same element, then I can obtain identical elements. So this kind of implies, that whenever these elements are distinct from each other, this list also is distinct from each other. Okay, so therefore the number of elements in GA is the same thing as the number of elements in AG, which is the same as the number of elements in A. Okay, I'm using this absolute value notation again, but just keep in mind that A may not be a group. So as a result, it's not the order that we have defined before. Okay, just keep this in mind. So by this, I'm basically saying this. Okay. But if I have the product of two sets, in that case, the number of elements in here is usually smaller than the product in here. And the reason is that I mean, in the product, of course, we have like the elements of the form like AI, BJ, and things like that. It is possible that, for example, let's say A1, B2 might coincide with A3, B4, for example, right? These kind of things may happen, in which case the number of elements in AB might be smaller than the number of elements in the products of the number of sub-elements, right? So in any case, what I'm saying is that in this kind of an expression, I don't claim that all elements are distinct. Probably they aren't. And so as a result, so we don't actually, I mean, this is something that we may want to be careful with. Okay, one example in here. If G is the group, in that case, G product with G is basically the group itself. I mean, this is basically the closedness property, but this is also true for infinite groups as well, right? But for finite groups, I mean, if a group has like n elements, there are like n squared possible products in here. So some of them should be the same with each other so that at the end, all possible products give you only n distinct elements, okay, obviously. If H is a subgroup, for the subgroup 2, H product with H is equal to H. Obviously, probably I shouldn't even add this as a statement in here. Again, for the subgroup, also we have this. So let me undo this. If I take all the inverses, then I get H. yeah, whatever. Okay, there's something called the rearrangement lemma, so that's going to be an important thing. So rearrangement lemma. This is basically the name given by Tung. I don't know if this theorem has a different name in some other textbooks. Okay, but this is for us, this is important. So G is a group, and little g is just an element in here. So rearrangement lemma says that the G multiplied with the group is the same thing as the group. Right, this is essentially what it is, okay? You can actually think of it as the statement of the lemma. Similarly, for the product from the right side, okay? Let me try to explain it like this. So suppose, right, let's just denote the elements of the group like this by labeling them like this is the first element, this is the second element, and so on. Probably the first element is identity, because when we actually list the group elements, we usually write the identity as the first element, okay? But it doesn't matter what it is, okay? So let me write this clearly. N is the order. Okay. So G is one of these things. So G is basically GI for some I. Okay. Whatever it is, it doesn't matter what it is. Okay. So G multiplied with the group is basically the list of elements in here. G of Gn. Okay. If this is indeed a finite group, then we have some kind of an interesting thing in here. Above, we have said that all of these elements are different from each other, right? Because this is a list of distinct elements. When I multiply from left with the same G, I get another list of distinct elements. But the group has only n elements, so as a result, all of these elements should be some kind of I mean, the same set of elements, but they are permuted, right? So as a result, this is, for example, GI1, that's going to be GI2, and whatever, this is GIN, but this list of elements is basically the same as this list, okay? Because obviously, since these are all different from each other, we should have the same elements repeated in a different order. Okay, you can actually think of it like this. Let's say it like this. Left multiplication by G. So that's the operation, right? Left multiplication by G is a permutation on G. Okay, so that's kind of important because we somehow identify group multiplication with some kind of a permutation. Okay, so yeah. So we will talk about this later because this is kind of important. So we will come back to this. So as a result, I'm just going to repeat this argument later. But just remember that a permutation can also be described as some kind of a function on an, for example, n element set. So for example, in any case, so I can actually think of this like a permutation might be like sigma Sn. So that's basically set of permutations of of n objects. Why did I call this as sigma? I don't know. Probably I should actually call this as I, for example. So as a result, this I might actually be considered as like I is mapping 1 to I1. So this element, I is mapping 2 to I2, and so on. I maps the number n to the in, for example. So what we are doing this is like, we are basically identifying, making a correspondence between a left multiplication by a group element with a permutation in Sn. Okay. So let's say it like this. We can associate every G in the group with a permutation I in the permutation group. Okay, so that's essentially some kind of an it's an isomorphism actually, but I don't want to go into the details in here. So let me actually remember this. I forgot the name of the theorem. Sorry about that. So I'll come back to this. Was it Cayley? I didn't actually write the name of the theorem. So sorry about that. So in any case, so let's say it like this. Every group of order n is isomorphic to a subgroup of Sn. Okay. In any case, so this connection between an arbitrary group, an arbitrary finite group, let's say, and a subgroup of a permutation group is kind of important for us because we are going to get a nice representation, matrix representation of the group by using this idea in here. Okay, so when time comes, we will talk about this, right, in some detail later. But this is like at the middle of the semester or something like that, right? Not soon enough. Okay. So the rearrangement lemma. So then we have, let's talk about some matrix groups. Okay, so the essential idea in here is this, right? A is an n by n matrix, let's say. So let's say A and B are, I mean, let's say A, B are n by n matrices. So they can be real or complex. Mathematicians also consider all the other possible other fields like the rational numbers and things like that. But in physics, we either meet the real case or the complex case. Okay. So in that case, A multiplied B is also n by n, right? So as a result, you can see a potential in here for defining new groups. But there's a restriction in here. If some set of matrices has to form a group, then they should be invertible, right? So therefore, A inverse must exist for defining a group. Okay, so also there's this identity in here, identity matrix. So it's basically the matrix where all the diagonal entries are equal to 1 and all the off-diagonal entries are equal to 0. So let me kind of show it like that. So that's the n by n identity matrix. Okay, I mean, we now have an explicit name for the case of matrices for identity. So I may not use the E notation in here. Just keep this in mind. In any case, we can actually form various matrix groups by using invertible matrices. So I'll just start with some general ones, and then I'll just go to some special ones. So the first one is called the general linear group of order n. So that's the general linear group of n by n matrices, right? This is basically defined as matrices A. So let's say it like this: A is n by n matrix with real entries, real matrix, with determinant A being non-zero. So the determinant is basically for invertibility, determinant condition. A matrix is invertible only if its determinant is non-zero. So as a result, we have this kind of a condition in here, in which case we basically have a set of invertible matrices, and this forms a group because we have inverses in there, the identities in there, the products of invertible matrices are invertible, and so on. So as a result, this is a group. It's called the general linear group. And so these are basically the first letters of this expression in here. And then we have the general linear group of, again, n by n matrices with complex entries, okay? So this is essentially the same as this group, but this time with complex entries. Right? So these are what we usually call Lie groups. Okay, basically, for example, in the general linear group of 2 by 2 matrices, we basically have matrices which are functions of 4 continuous parameters. There's just an added restriction in here, is that this determinant expression should be non-zero. But this is just an exceptional situation. In general, I mean, all of these 4 numbers are kind of arbitrary. You can change them continuously. So let's say it like this. Every element of the group depends on 4 real parameters. Okay. There are some exceptional points in there which are not within the group, but that's not an important detail. So as a result, this says that the general linear group is a 4-dimensional Lie group. What's a Lie group? I'm not going to say much in here because the definition is kind of complicated. Let me just say it like this. Group elements depend on continuous parameters. Okay, and group operations are smooth functions of these parameters. Okay, let me just say it like this. What is smooth? It basically is differentiable. Infinitely differentiable, in fact. It's not just a differentiable. I mean, continuity is not an enough requirement. We also, continuity with respect to these parameters is not an enough requirement. We also need some kind of a smoothness and things like that. In any case, at least for that group, for example, you can see that the product of two group elements would actually be continuous with respect to the entries. Inverse also satisfies the same property. So these kind of group operations, if they are smooth functions of these parameters, then we say that this is a Lie group, okay? So it's just a term that comes up frequently. So as a result, I would like to define it like this. Basically, all of the groups that we are going to see that somehow where the group elements depends on some kind of a continuous parameter, these are going to be Lie groups, like the rotations, for example, where the rotation angle would be some kind of a continuous parameter. In that case, the rotational group would be a Lie group. Okay. So if you go to particle physics, then these are the groups that you're interested in, basically. And the representations of Lie groups and things like that will be very important for you if you are going to do particle physics. Unfortunately, this is a very complicated subject. So in this course, we are not going to do this. So basically, in this course, we are going to do the representation theory of finite groups. Okay. Perhaps at the end of the semester, if I have like enough time, I can talk about the rotation group and its representations in a way. But probably not. Probably I will just talk about the angular momentum algebra in there. I mean, if we have time. In any case, I mean, let me just mention this in here. Then let's pass to the other groups. So first of all, right, note the determinant of AB is the same thing as the determinant of A and the determinant of B. If it happens that if the determinant of a matrix, if two determinants of these matrices are both equal to +1, then their product also has a +1 determinant. And this basically enables us to constrain the general linear group. So just include only the matrices with determinant 1. In that case, we get what we call as the special linear group. Right. So these are basically, A is all n by n real matrices where the determinant of A is equal to +1. Why do I say plus? It's equal to 1, right? So since the products of such matrices also have determinant 1, this is actually a subgroup of the general linear group. So it's called a special linear group. Okay. Right, so SLNR is a subgroup of the general linear group. So in this way, we can actually define some other subgroups like that. So in a similar way, I can define the complex version of this, etc. Right? Okay. Let me then go to another subset of these. There are these two kinds. One of them is called the UN. I don't use any complex number this time because these are assumed to be complex. So let me just say it like this. So this is basically matrices A where A is n by n complex. A is unitary. So that means A inverse is equal to A Dagger. Okay, let me just say it like this. A is unitary if A Dagger is equal to identity. Okay. Which implies that this is the same thing as A Dagger A being equal to identity, which implies that this is the same thing as the inverse of the matrix is equal to its Hermitian conjugate. Right? if it happens that if A and B are unitary, so is their product. Basically because AB multiplied with its Hermitian conjugate is, well, Hermitian conjugate basically is an operation that changes the order of the matrices. So as a result, you get something like that. And BB Dagger product gives you identity. So you get like AA Dagger, which also gives you identity, right? So as a result, the product of two unitary matrices is unitary. And therefore, this is a group. So this is called the UN is called the unitary group. I think I'm going to give a break in here. Let me stop first.